All right, our last example here is you have some kind of like board or beam or something. You have cable 1 attached right at the end point here. And you have cable 2 3 meters away from the left. This is the left end point and this is the right end point. So this is 3 meters away from that. And the board as a whole is 4 meters long. So get that picture drawn down. Those are your givens. And I'll say the weight of the board is 1,000 newtons. If this whole board is 4 meters, where does gravity appear to be acting at? Right in the center of the board, which is right at 2 meters. So just keep that in mind as we solve for things here. So the givens are this situation right here. And you can picture, before all of our questions are very symmetric. So we're like, oh, maybe it's splitting the cable. This is FT1 and FT2. Maybe they're equal because they're on each endpoint like that. But the reason this is different is because you have a cable attached to the left end point, and you have a cable attached 3 meters away from that left end point. So we're going to solve for the tension in cable 1, and we're going to solve for the tension in cable 2. And we're going to do our 5 steps for success, and it'll make sense. I almost should have called this example 3 because I think this is a notch easier than the one we just did. So step 1, we drew our picture. Step 2, we're going to label our forces, and we'll take care of that right now. So if I'm the board right here, I'd say FT1 is pulling up. I'd say FT2 is pulling up just like that. And if you ever had 2 upward forces and you're like, whoa, this thing's in equilibrium, that can't happen because if you had 2 upward forces, it'd be moving upward, right? So there has to be a force pulling downward, and that's the gravitational force of the board right there, Fg. And just be mindful, this whole board is length 4. Fg of the board is happening right at 2 meters away, and we'll talk more about that, okay? And I've not drawn this to scale. I'm just a lefty who's a little bit messy. So step 1, we drew a picture. Step 2, we label our forces. Step 3, we have to choose our coordinate system. So I'm just going to use the standard xy. Now, this question, just like our previous question, it's in equilibrium. This board's not moving, it's just hanging out. And so we have the board, we have 2 forces up. So we're doing our 5 steps for success. Step 1, we drew a picture. Step 2, we labeled our forces. Step 3, we show our coordinate system. But remember, with torques, there's another part of step 3, we have to pick our point of rotation. And I'm just going to pick it at the left end point. That's where I'm going to reference my torques relative to. That's the 0 point, r equals 0. Now, just to reiterate this point, when you're in equilibrium and you don't know exactly what the point of rotation is going to be, you could technically pick your point of rotation anywhere. And as long as you're okay relative to that, you keep consistent, you get consistent answers. But the big thing is this. I like to pick it at the left end point because that's where I'm calling r equals 0. Okay? So we have that going on. So picture forces coordinate system. Part of the coordinate system step now, we picked our point of rotation. And now we're going to sum our forces. So let's go ahead and sum our forces right now. So we're going to sum our forces at step 4. And we're going to do it in the y direction. And in the y direction, we have FT1. Now, on our last question, we had a hinge. This is not a hinge. This is straight up a board with a rope pulling up and a rope pulling up here. There's not like a hinge, like a metal hinge or anything. That's just cable, gravity. So this one actually is a hint more simple than the last question. So we have a force tension 1 pulling up. According to our coordinate system, up is still positive. FT2 is also pulling up, FT2. And if you stopped right there, you should be like, oh, that doesn't make sense because we have 2 forces pulling up, but we're in equilibrium. So you have to have a down force, and that's our gravitational force right there, minus force gravity. And remember, this is a result of Newton's second law, F equals m times a. And the only thing is, there is no net force in the y direction. So if you have 0 net force, that means you have 0 acceleration, the net acceleration. So this is 0 newtons, just like that. So kind of a cool thing. They told us force gravity is 1,000. That's about, that's about how much I weigh. So it's a pretty dense board. We don't know FT1, we don't know FT2. So we have 2 unknowns with 1 equation. Okay, so we're like, okay. And if you want to write, I plug some numbers in here just to kind of make it look a little bit prettier for a second. I'm at a big number, plug your in there. So that FT1 plus FT2 equals 1,000 newtons. And if you draw good FBDs, you already knew that from the get-go because those 2 upward forces have to balance that downward force because it's in equilibrium. So we know that, okay? And then you're like, okay, well, Laurent, you said some of your forces is in the y, some in the x. Well, here's the bummer about the x. There's nothing happening left and right. So you just set it equal to 0 newtons, and you're like, oh, that makes me feel good. Maybe a little sad, but mostly good because that's true fact. So the last tool you have, step 4, we summed our forces in the x and the y. Now the new step is we have to sum our torques. And we're going to do that right now. You sum your torque, and I should have given myself more space, so sorry about that. And it's all relative to your point of rotation. So I picked my point of rotation to be the left end point right there. Now here's the cool thing. Sometimes it's convenient to pick your point of rotation where you have the most forces acting because remember, if I call that my 0 point right there, FT1 is not going to be causing any type of torque because that's like you pushing on the hinge. You're putting a force, right? R equals 0 right there. So if you ever have, remember our last question when we had a forced hinge in the X and a forced hinge in the Y, and we said, well, they don't have any torques. That was actually pretty helpful because we had two forces that we didn't have to account for when we were doing our torques. So if you don't get that reasoning right now, I'll just say it a little more shortly. When you pick your point of rotation, when the problem's in equilibrium, sometimes it's helpful to pick one where you have multiple forces acting, just because then you don't have as many torque contributions to add up. But if you don't get that for right now, you're like, whatever, I'm just going to pick the left endpoint. That's A-okay as well. If you're just going to pick the hinge, A-okay as well. In this equilibrium question, we're not sure where it's going to rotate about. It could rotate about here, here. So I just picked the left endpoint. So sum of the torques. FT1 is not causing any type of torque because it's got an R of 0 because it's right at your point of rotation right there. So no torque contribution to add in right there. The first thing that's causing a torque, gravity is acting. This is 2 meters away from your point of rotation and it's acting that way. So if you're going to use your right hand rule, you stick your fingers with the lever arm R and you curl with the force. And you can picture force gravity is trying to make this board rotate clockwise. And clockwise torques, they call those negative. So we say force gravity. A lot of people say, I'm summing my torques, and they put a force right there. To turn a force into a torque, you have to also times by the lever arm. In this case, force gravity is acting 2 meters away from that point of rotation. Now, really important, gravity is acting straight down. This lever arm is straight to the right. That angle is 90 degrees between your R and your force that you're applying right there. So it'll be the sine of 90. So gravity's got maximum torque right there because it's pulling straight down. The lever arm is right like that. And it is a negative torque because remember, R force to curl. This force is trying to create a clockwise torque, which is negative. That's just how they define it. Clockwise is negative, just like the unit circle. Now, we have one more torque because if we just had this one torque on there, this whole thing would be rotating clockwise. But we know it's in equilibrium, so there must be a torque that's balancing in the opposite direction. And it's FT2 right there. So FT2 is 3 meters away from your point of rotation right there. Put positive, and I'm going to put FT2. Once again, that's just the force. To turn a force into a torque, you have to times by the lever arm, which is 3 meters in this case. 3 meters. And then this FT2 is going straight up. The lever arm is going to the right like this. So that angle right here between the R, and I don't like marking up my diagram, but between my R and my force is 90 again, so it's a sine of 90, so it's got maximum torque, 90 degrees. And this beam is not rotating. So if the beam's not rotating, we know the net torque has to be equal to 0 Newton meters. And I'm out of space, 0 Newton meters. Okay, it's an equilibrium. The forces and the torques add up to 0. Now we're looking at this and we're like, oh, the force gravity was 1,000 newtons. There's a negative right there, times 2 meters. The sine of 90 is just 1, so I'm not going to write 1, plus FT2 times 3 meters times the sine 90, which is 1. I'm just going to rewrite this a little bit. FT2 equals 0 Newton meters of torque. And you're like, oh, okay, 2 times that is negative 2,000. Add it over that side. So you're going to get 3 FT2 equals 2,000 Newton meters. So you're divided by 3 meters on both sides. 3 meters. Meters go bye-bye. So FT2 equals 666.67 newtons. FT2's got 666.67 newtons. And you can reason, you know that FT1 plus FT2 has to equal 1,000. So you're like, okay, now that I know that, I'm going to go back. I'm just going to solve for it. Your reasoning says it's 333.33, but you can show it right now. FT1 plus 666.67 newtons equals 1,000 newtons. You found FT1 equals 333.3 newtons. So this is about 667 newtons. At least it's about 333 newtons if we just round to the nearest whole number. So that kind of makes a ton of sense because this left cable right here, he only has 333 newtons. You can picture this center of mass of the board is closer to FT2, so there should be more tension in that cable. It's only 1 meter from there. Here, it's 2 meters away from FT1, so there's less tension in that cable. So if you're on a multiple choice and you had to reason out, hey, which cable has more tension? Well, obviously, the one that's closer to the weight of the board, where the weight of the board is, that would have more tension in there. So the big thing is you take your two tensions, they should add up to what we had right there, and they do. That's your 5 steps for success. We drew a picture, we labeled our forces, we picked our coordinate system, but we also had to pick our point of rotation, which we just picked at the left endpoint. We didn't know for sure because this thing's not moving, it's in equilibrium. We just said we get to pick it, and I picked it left endpoint. And then step 4, we summed our forces, and we said that helped us, but we still had too many unknowns, so we also had to sum our torques. And remember, a lot of people sum their torques, and they just put forces down. To turn a force into a torque, you have to times by how far away that force is acting. So that gravity was 2 meters away from your point of rotation right there. We summed up our torques. We got our tension 2. And once we do tension 2, we just work backwards and solve for tension 1. So that's torque. That's about as tough as it gets for a while. Just follow your 5 steps for success and it'll be a great starting point for you. Thank you very much.